Okay, everyone, so welcome back. So last time I was still discussing Leibniz and his contribution to math. So I wanted to say a couple more things about that before I'm talking about some of his contribution to the philosophy, and then moving on to 18th century mathematicians. So as I'd mentioned last time, if you're thinking of an infinitesimal uh, and specifically in the computation of the derivative of a function, right? The way this was written was the dy. If y is described as some function in terms of x, the dy was thought of as f of y plus that little infinitesimal bit dx minus uh, this is not y, f of x plus that little infinitesimal bit dx minus f of x here, right? And the derivative, like once we had computed this thing, the derivative that Leibniz obtains was this quotient. And in Leibniz's sense, this was a literal quotient. It was dy, which was a separate infinitesimal thing, divided by dx, which was the separate infinitesimal thing. These were two infinitesimal quantities, and you were literally dividing them, so this was a quotient, was dy over dx here. Now, the way that this is done, right, in the modern sense is as follows. So this wasn't put on rigorous footing, as I mentioned, until the late 1800s. So this wasn't put on entirely rigorous footing uh, until the late 1800s. And it's not just that infinitesimals themselves weren't put on the rigorous footing. So it's not just Leibniz's work, I should say. It's that the all of the work that relied on it, and all the mathematicians that came later who were using Leibniz's notation and who were computing in the same way that Leibniz did with these things, technically that was not on rigorous footing. There were some other things that weren't exactly related to infinitesimals that weren't rigorous also, that were fixed at the same time by the same guy for the most part. Um, so as I mentioned before, they mathematicians at this time and all the way up to the late 1800s weren't terribly concerned about convergence arguments when it came to dealing with these infinite series. And so they did some very hand wavy and not quite rigorous things when it came to computing with these series, particularly when it came to rearranging the series. They didn't quite understand what was required to make that rearrangement work out the way that they thought it always did. And so that is something that was not put on solid footing until Karl Weierstrass, as I mentioned last time, was kind of the main force for putting all this on rigorous footing. And he is many times referred to as the father of modern analysis. And analysis is the word that we now use to describe calculus, or I should say that the calculus you know of sits inside a field called analysis. And so calculus style quantities that are studied in math are grouped into this larger subject of what's called analysis. So he's called the father of modern analysis because he was the first to put it on completely rigorous footing. And so what this does is it treats dy dx as not a literal quotient, but rather a limit of quotients. Okay, and so this dy dx is treated as you have seen the limit of this difference quotient before if you've taken calculus. So you say let this be the limit as h approaches 0 of f of x plus h minus f of x over h. All right. He was the one to write this out. This makes rigorous this notion that was being expressed here, and it not only makes it rigorous by bringing in these limits, but it also makes the notion of limits rigorous. So where limit is defined using the epsilon delta definition of limit. So if we do more on analysis, right, according to the class poll, analysis is currently in the lead, although because it's split the way it is, I may not, ignore the others. I may kind of try to touch on all those three things. Since no one said that they were fine with anything, so yeah, I may try to touch on several of those things and just mainly focus on analysis if that is the thing that wins. But so I'll revisit this if we talk about analysis later. But this is using the epsilon delta definition of limits. Depending on when you took calculus and your particular instructor, you may have seen this when you first learned about it. It's not always super useful to teach someone first learning calculus the epsilon delta definition, because they're likely going to be very confused by it, because when you are taught about limits in the first place, you are typically going to think of limits in terms that are not entirely rigorous. Things like when you think about approaching, you think about being very close, or you think about h being a very small quantity, right? And dividing by a very small quantity being a very big quantity. You're going to use terms like that, and you're not going to be 100% rigorous. It's a little vague. But limit is defined using the epsilon delta definition, which completely makes rigorous the notion of a limit. Okay, and suddenly, once you have this way of defining a limit, you have a way of mathematically 100% rigorously describing a quantity that approaches or gets arbitrarily close to some object or some value. So this is the full resolution of Zeno's paradox. Right, so go all the way back to Zeno's paradox and his arguments against motion. Right, many of them relied on some weird interaction between approaching. Right, there was Achilles and the tortoise. Right, or some of his other arguments against motion involved these. It was really a problem. Fundamentally, it was a problem with infinitesimals in some way. Okay, it was a problem with the notion of approaching, right? His problem wasn't necessarily with infinitesimals in the small sense. It was a problem at infinity, right? Was the problem of some of Zeno's paradoxes. But finally, Weierstrass puts this on completely rigorous footing, and so modern analysis is done in this way. And underlying this, even if you didn't specifically use the epsilon delta definition to compute limits, underlying how you treat limits is the epsilon delta definition. Did Leibniz and friends believe that what they were doing was sufficiently rigorous, or were they not concerned with rigor? So as I mentioned last time, Newton at least was a little bit concerned that his infinitesimals, I don't know that he believed whether or not they were 100% rigorous, or that he couldn't exactly show that they were 100% rigorous, but I think he was mostly convinced that people might be upset by them. Some people might not believe them. So Newton was at least aware of that. I think they were less concerned. It's not that they were concerned that there was an issue. It's more that they were happy that they were getting these results. Right, and it's a bit like if you come up with some mathematical approach to, say, solving a particular equation, right? Solving a cubic, right? If your justification for that approach might be a little shaky, but every single cubic you sit down in front of you and you try to solve using that method, you can do it, and you can check, and you can see that, like, every single cubic I've applied this method to, it worked. Right, then you're you do kind of have the attitude of, well, I don't necessarily care that it's not that rigorous because it works, right? And if something works, then I don't mind so much, right? I don't mind so much that maybe there's a problem in the foundation. And I think it was more that they were getting results. They were getting results that could be checked, right, against how things should be, and it came out all right. So the rigor didn't matter so much. The same thing is going to be true. I don't think I'm going to have time today, and I may save it for the analysis if we go in that direction. I may save it for the analysis bit. But there was a famous problem that a great mathematician, Euler, solved called the Basel problem. And the argument that he used is technically not 100% sound and rigorous because of this issue with power series, and him not treating the convergence and him being able to just rearrange stuff the way he wanted to. The way he did it was not 100% rigorous, but he got the right answer, right? So, if he were doing that in a proof course, he might have gotten points taken off for his proof. But he did ultimately get the right sum. He got the right answer. So it's kind of, him getting the right answer or them getting these results was kind of evidence that even if their method wasn't 100% rigorous, it was right in some way, right? In some overall way, it was correct. What they were doing, or at least the central idea was correct. Okay. In fact, it turns out that, and I've mentioned this, I think, at the very beginning of class, like at the very beginning of the course, I should say, in like the first or second lecture, that infinitesimals can actually be added to the real numbers in a coherent way. So infinitesimals can actually be added to the real numbers. In a consistent and coherent way. So I'm talking about logical consistency and logically coherent, not necessarily coherent in the sense of, easy to understand or anything like that. So this was done in 1966 by Abraham Robinson, who's an Israeli mathematician. He showed that you could come up with a what is called a nonstandard model of the reals, which leads to nonstandard analysis. Okay. And in this non-standard model of the reals, he adds in a quantity that we'll call it Cassi. Okay. So Cassi. Oh, that's a bad Cassi. Here, let's make a better Cassi. Okay, that's a little bit better. So he adds in a quantity Cassi such that this Cassi is between 0 and 1. No. There. So it's strictly between 0 and 1, but also it is strictly between 0 and 1/2. And it's strictly between 0 and 1/3. And it's strictly between 0 and 1/4, and so on. Okay. So he adds in this quantity, this infinitesimal quantity. It is different from 0, but it's small. How small? It is, well, it's smaller than all of these fractions I'm listing out. Okay, so it is infinitesimally small, but it is not 0. Okay. And it turns out this can be done in a way that doesn't introduce any contradictions. Okay. I may present that argument, like I said, if we go in this direction. I may talk a little bit more about this. But the neat thing is not that this is necessarily a great way to do analysis. This leads to a very weird system. So non-standard analysis is an entirely different thing, and it's a strange world. And the way that it had to be done here, there's a reason why it took so long for someone to do something with this. The way that it had to be done is not easy to understand. It's not intuitive or anything like that. Whereas Leibniz's way of dealing with infinitesimals, it wasn't rigorous, but it was very simple and intuitive. This is 100% rigorous, but it's not simple. It's not intuitive. So it doesn't have those benefits, and it leads to kind of a strange way of doing things, but it can be done. And that's the important and interesting thing, that actually the way that Leibniz was doing things with infinitesimals is not just some totally made up and totally wrong thing. It can actually be made. Infinitesimals themselves can be made rigorous. So it's pretty interesting. This is a pretty interesting fact. And I should say that it's not non-standard analysis has led to results in standard ordinary analysis. So it's not something that has like no purpose or further application to maybe the more normal analysis, normal calculus that can be done in the usual way without infinitesimals added in like this. Okay, so that's pretty much covers what I wanted to mention about Leibniz's contributions mathematically. Now what I want to talk about is philosophically. So Leibniz's philosophical contributions. And probably those philosophical contributions. Probably the most common thing that you hear whenever Leibniz is brought up in the context of philosophy has to do with Leibnizian optimism, right? So you have likely heard this expression before. So Leibnizian optimism. So the most classic thing that you hear associated with Leibnizian optimism is the assertion, we live in the best of all possible worlds. Or the best of all possible universes. Okay. And of course, this was made fun of a lot by other philosophers that came later in the 18th century. So Voltaire famously made fun of this. Candide was basically lampooning Leibnizian optimism. So there was the Lisbon earthquake in the 1700s. Was a huge shock to European kind of scientific establishment, because it was this horrible thing, this horrible event that had occurred, and it kind of shattered any very literal reading of some kind of Leibnizian optimism type argument that we live in the best of all possible worlds. But as much as this has been made fun of by Voltaire and others, it's not really what Leibniz meant in terms of best here. Right, the question is, what does best mean? Leibniz clearly, he wasn't, Leibniz was clearly not a stupid guy or completely sheltered or anything. He understood that, could the world be made a happier place, right? Could you take current world and improve overall happiness? Well, of course, right? Even trivially, you could see that's the case. So best here does not mean happy. All right, so then what does best mean? Well, Leibniz specifically referred to Snell's law. So Leibniz specifically referred to Snell's law repeatedly. So in his work, this is a Discourse on Metaphysics. So in Discourse on Metaphysics, he refers to Snell's law. Explicitly, Snell's law is the law concerning reflection of light. Sometimes called Snell-Descartes law or Descartes' law, but usually it's just called Snell's law. So if you have light rays, right, and let's say that I have two different substances, right? So I have substance up here, and I have some substances made of something else here, and I have light rays that are coming in this direction, and they hit this substance. So they hit this surface, right? This boundary of this region, whatever substance that is. Well, the way that the refraction of the light rays is governed is that rather than the light rays continuing on in some line like this, right, or like straight on this line, they are refracted, and the way that they're refracted depends on basically the minimum. It's like the minimum path, right? This becomes a piecewise line instead, or a piecewise linear curve instead, because the second that this other material is interacted with, the second that your light rays intersect this, well, now if I'm breaking this down into points, right, light rays are going just the shortest distance from this point to this point, but now the shortest distance is altered. Okay, and it's not that I'm talking about the shortest distance just geometrically. This is impacted by whatever this material is made of, right? And so this is like it's like a path of least energy, or an energy efficient path. Okay, this is related to kind of an overall notion of like a principle of least action, right? Which is a way of, it's kind of a principle that puts forth the notion that a physical process happens in such a way as to minimize the action. That is some integral involving energy. Okay. And so Leibniz specifically refers to this repeatedly in Discourse on Metaphysics. And so it's more likely that Leibniz specifically meant best as most energy efficient or most efficient. So most efficient in energy, or in just some kind of like overall cosmic way. So best here is meant to refer to like the physical properties of the universe, rather than say the happiness of some particular citizen, or the happiness overall of the world or the universe, right? Okay. And so, this Leibnizian optimism statement that you might have heard a bunch is not quite as ridiculous on its face as you might have, originally thought if you just have the most literal reading possible. Leibniz was not quite saying that. He was more saying something about fundamental physical properties. So it's most efficient. The universe of least action, or something. Okay. So one other thing I wanted to mention about Leibniz's philosophical contributions, and I think this is definitely worth a look if you've never read this. I recommend it because it's very interesting. Leibniz wrote a work called the monadology. The monadology, or monadology, is probably, well, not probably, it is his most original contribution to philosophy, because there's not really anything quite like it in terms of how he tries to lay out like a metaphysical foundation of the universe. So he wants to define the universe in terms of monads. So he describes the universe in terms of monads. These are elements, okay? So these are the elements that make up the universe in the monadology. Um, so they are almost like a primitive, undefined concept. They only have a couple of properties. So they basically could be thought of as like points. Okay, and I'll talk a little bit more about that in a second. But Leibniz said that souls, human souls, are an example of monads. They're monads with memory and reason. So to Leibniz, souls are monads with memory and reason. But the thing about these monads is that they are kind of like these blind elements of the universe that Leibniz says the monads have no windows. So his idea, and other later philosophers have said similarly, that monads can be thought of as points. Because think about it, right? Like, what is a point in geometry? Like, how do you describe what a point is, right? Without drawing it, what is a point? Well, it's kind of hard, to describe what a point is. In fact, Euclid took the point to be it's this primitive, undefined concept, right? So it is kind of like this zeroth level quantity that is almost like this inherent, implicit quantity that needs no definition. It's so primitive and primordial, right, that there's no definition of a point. It just is. Okay. So this is kind of how Leibniz's monads are, but his monads are not just the points, but they consist of points and arrows. Okay, both arrows from point and arrows to point. Okay. All right. So what was the idea behind this type of picture, this type of thing going on? The idea was that the monads could be thought of as kind of points in space, but not just the points, but also some kind of like small neighborhood of points around that point. And these arrows were defining some kind of relation between different monads, right? So a monad related to every other monad in the universe in some way, in arrows going out and in arrows coming in. Okay. Now, there's a couple of things that you can think about here. So both Abraham Robinson that we mentioned earlier actually uses monad in his definition of nonstandard analysis, or in his work on nonstandard analysis, I should say. So in his work on nonstandard analysis, monad is an actual quantity that is used. It's defined in kind of a similar way. Bertrand Russell wrote about this in the early 20th century, and he also basically gave a similar description of monads as these points and arrows. Now, there's a couple things I wanted to say about thinking of the universe is made up of these monads that consist of points and arrows. One, if you've seen anything concerning graph theory, then this might remind you of some kind of like graph-like object, okay, where you think of a graph as being a bunch of nodes, and those nodes are connected by, so the nodes are points here, and the nodes are connected by these edges, right, between some number of nodes, right? And there's all kinds of different properties that graphs can have. Graph theory is a huge entire subject on its own, has tons of applications all over the place. But, so graph theory is closely tied in with combinatorics and combinatorial arguments, combinatorics is the mathematics of counting, right? And that if you've never heard of combinatorics before or seen any combinatorial arguments, that might not sound too interesting to you. But combinatorics is really, really interesting, and there's very, very complicated stuff that involves combinatorial arguments are can be extremely beautiful. They can be really, really complicated. I mean, they kind of fill out the spectrum of what you can see in math. So finite math can be a lot of fun. I'm actually terrible at it. I'm like my intuition is absolutely garbage when it comes to most finite math stuff. But I'm friends with a lot of people that are very, very interested in finite math and are very good at it. So I get to hear them talk about it anyway. But anyway, there are you might see when you look at things like a graph or these combinatorial defined things, you might have a tendency to kind of think they belong maybe to the realm of like computer science or things kind of more in that direction of applications. But even there are some very deep things that have been proved in theoretical physics that involve these weird kind of black box, almost combinatorial type arguments. So the Witten conjecture. So the Witten conjecture was posed by Edward Witten, I guess originally maybe in the 80s, late 70s, something like that. It was proven. I'm not going to state it or anything. It's very complicated and it would take me forever. But it was proven in 1992, I think, by Kontsevich, and his proof of it relied on computing these integrals on ribbon graphs. It was a very combinatorial type argument, and it's not the only example of combinatorics and these weird graph theory things coming up in unexpected places, even when it's discussing things in like theoretical physics and cosmology. So the notion that the universe, might be made up of graphs or might be a graph in some sense is not too insane. So maybe Leibniz was onto something there. The other thing that this relates to, when you see points and arrows between points, this relates to the mathematical notion of a category. Okay. So this is a mathematical notion, I'm not just saying the word category there. The mathematical notion of a category generalizes or makes more rigorous it's a different thing, but the category is a construction that lets you talk about sets that otherwise would be really funky. So in the poll that I sent out to describe the foundations or logic subfield, I posed the question, does the set of all sets that contain themselves contain itself or not? This is known as Russell's paradox, also named for Bertrand Russell. So Russell's paradox poses this exact question. The answer is there is no answer using naive set theory. In fact, Russell's paradox showed that there was a foundational problem in the set theory and the logic that was done at the foundation of math, because the answer is you can't answer it. It contains itself and it doesn't contain itself. There's a logical contradiction. So it's a problem. And to fix problems like that, the notion of category had to be defined. So I'm not going to get into exactly what a category is, but it is a way of defining some of these tricky things that you might want to talk about. So you might think that, like, who would want to talk about the set of all sets or the set of all groups or the set of all spaces of a certain type? But you do at various times. And without a way of talking about them in a rigorous way, you're stuck in the land of Russell's paradox, where you're not quite sure exactly if you're on solid footing. Okay. So, but the monadology is a pretty interesting read. But that's pretty much all I wanted to say about Leibniz. So there was a ton of stuff to say there, but this brings me to the 18th century, where um, as I have already mentioned a bunch, here's the cutoff point. Because after Newton and Leibniz and the discovery of calculus, there was an absolute explosion of developments. They were happening simultaneously all over Europe, and they were happening and splintering at such a rate that it's very, very hard to group all of the mathematical innovations that were occurring. So this is kind of I'm going to make this like a circled star here to say, like, this is the point. Up until this point, we have proceeded through history basically keeping track of almost every major mathematical development, right? From the dawn of time, right? From the dawn of history, all the way through to the discovery of calculus, we more or less accounted for every major idea jump. Right. Here's the first time that we are going to have to stop that, and we're not going to be able to account for every single bit of progress that was made in every part of math. So here's where that stops, and unfortunately we have to cut a lot of the discussion because it would just take too long. It would take far too long to go through all the innovations as they branched out, and we're quickly approaching a time when, as a general math class, or a general history class even, for a more general audience, it just becomes impossible to cover these topics because they get too complicated. And they don't get too complicated just for, say, someone who's, not a math major or minor or something. They would get too complicated for undergraduate math students, period. Because you're starting to, by the end of the 18th century, you're already on topics that are beginning to approach, depending on what field you're in, they're beginning to approach like things that are covered at the graduate level. So it's fast advancing here is what I want to get. And so for that reason, we have to make some sacrifices. So what we do is we attempt to pick out the big names. Okay, and so here's a few of them in the 18th century. This list, certainly not exhaustive. It is not only not exhaustive, it doesn't even cover all of the important innovations that were made in math during this time, but it covers a lot of them. So the first name, Brooke Taylor, who was a big fan of Newton, and used his love of Newton to come up with the series that is named after him, so he is well known for the Taylor series. Colin Maclaurin is also known for the series that bears his name, which is really just a Taylor series special case. It's the case when you're expanding about zero. So if you remember Taylor series, I'm about to write those out now. But the Maclaurin series is just the Taylor series expanded about zero. There's Abraham de Moivre, who is primarily known for a single formula that he was the first to write out. He's actually kind of a tragic case because he was very talented, but he ultimately basically spent most of his life being just a private tutor and answering questions from professional gamblers about probability, which was fine, but he could have done a lot more. So Leonard Euler, that you have no doubt heard of before, at least he has a very popular constant named after him, Euler's number, right? So Leonard Euler, probably the most prolific mathematician of all time. He probably is responsible for a greater bulk of mathematical contributions than any other single mathematician in history. Even Archimedes, right? Because Archimedes was not really the most prolific. We have very little of Archimedes' work that survived in full, so it's actually hard to say. But even so, wide range of Euler's contributions are it is actually amazing. So probably the most prolific mathematician in history. And he almost certainly published more than anyone else. So he published an absolutely absurd amount of papers. And he standardized a lot of notation as well that still gets used. That wasn't in use at the time of, say, Leibniz. There's a lot of that notation is responsible, or Euler's responsible for. So Lagrange is the next on the list. So Joseph Louis Lagrange, if you've taken Calc 3, then halfway through Calc 3, you must learn about Lagrange multipliers. And Lagrange was the one who first used this method. Was he the one who first used this method? I'm not sure if he was first, but they're named after him nonetheless. Okay, so Laplace is next on the list. Pierre-Simon Laplace. If you have taken differential equations, then you have learned about Laplace transformations. So Laplace was the discoverer of the Laplace transform. He was also... Laplace did a ton of stuff. It's kind of hard to name everything. If you're familiar with partial differential equations, he was responsible for the operator known as the Laplacian. Also, if you've had Calc 3, the Laplacian can be thought of as the divergence of the gradient. So view the gradient as a vector field. The divergence of the gradient is the Laplacian. That defines Laplace's equation. The solutions to Laplace's equation are called harmonic functions. The study of harmonic functions is called harmonic analysis, and that's a really, really important thing. It's a really important field. Has a lot to do with the study of signal processing and well, a lot more than that, but that's just one application I can think of off the top of my head. And then Legendre is the last that I want to mention in this group. So Adrien Marie Legendre. And so this is 1752 to 1833. Legendre was primarily known for his contributions to number theory. So there's a symbol you might not have heard about before called the Legendre symbol, and it is used to compute this quantity that it is the subject of a very famous theorem called the law of quadratic reciprocity. And if I have time, I might end up stating the law of quadratic reciprocity and kind of giving you some examples of why the law of quadratic reciprocity is nice. Kind of my easy way of trying to explain this is we have encountered modular arithmetic coming in the form of our work with the Chinese remainder problem. And the Chinese remainder problem has something about solving these linear congruences. The law of quadratic reciprocity, which was originally formulated by Euler, but not proved by Euler. It was first proved by Gauss, which is a mathematician that's not on this list right now. He comes a little bit later in the 1800s. But the law of quadratic reciprocity has to do with solving quadratic modular equations. So it's not the greatest analogy, but you can think of it almost like a quadratic formula for degree 2 modular arithmetic, I guess. Is that the worst analogy ever? Maybe not. I think that's fine. Okay, so anyway, I have a few minutes, so I'm going to start. The first three won't take too long at all. Euler will take significantly longer because he did a ton of stuff. And so that will probably be mostly the topic of the next lecture. I will tidy up the last three after that, and then we will be on to whatever topic has won the poll or some selection from the topics if the spread remains as even as it is now. Okay, so here's my list of 18th century mathematicians that I'm going to go over. All right, so what about Taylor? So Taylor, big fan of Newton, and he discovered the Taylor series. So what is the Taylor series of a function? So if I have a function and I expand the function about the value a, right? So I have my function f of x. If I think about expanding this function about the point a, well, a way of writing this function in maybe a little bit more creative way is f of a plus x times the derivative of f at a. So prime is denoting derivative here, plus x squared times f double prime of a over 2. But I'm going to go ahead and write the actual pattern here. That's 2 factorial plus x cubed times f triple prime of a over 3 factorial plus x to the fourth times the fourth derivative of f at a over 4 factorial, and so on. So if I write this using summation notation, this is the sum from n equals 0 to infinity of f this n in parentheses means the nth derivative of f at a over n factorial times times x to the n here. Okay. All right, this is the Taylor series. And Taylor proved what's called Taylor's theorem, which shows that basically every reasonable function, right, satisfies this. So I can expand most functions into. This is technically wrong. It's not most functions, but that's why I put most in scare quotes here, because it's most functions that I'm interested in right now. Okay, it will turn out, of course, that you can't do this for most functions in a strict sense, but I can expand most nice functions into a power series using this fact. Why is this so nice? Well, we began our study of like the theory of equations, right? Trying to study polynomial equations. So linear equations, quadratic equations, even the Babylonians knew how to solve quadratic equations, right? It wasn't until Tartaglia and Cardano that we could solve cubic and then quartic equations, right? Those are all questions about polynomial things. So polynomials were the first functions that we thought of. And once we have Descartes coming along with analytic geometry and we come up with the notion of, the modern notion of function in this same way, well, now what? Well, now we would very much like it, right? Just going all the way back to Cavalieri's formula and Wallace's work after Cavalieri being able to compute the area under a polynomial. Polynomials are the nicest possible functions that we can deal with, right? And so if we could turn every function into a polynomial, we are very happy, because we know that, functions like exponential functions, logarithmic functions, trigonometric functions, these are not on their face polynomials. Okay, in fact, they're not polynomials at all, but they can be expanded into Taylor series. Okay, so they can be expanded into Taylor series, and because they can be expanded into Taylor series, while they're still not polynomials, they can be thought of as infinite polynomials, right? So a power series is an infinite polynomial, an infinite degree polynomial. That's what a power series is. Okay. And so, this basically allows me to treat a generic function that might not be anything like a polynomial on its face as a polynomial in some sense. Okay, so this is a very nice thing. All right, so I'm going to stop here with this, and I'll continue on that list of mathematicians. My next lecture will mostly concern Euler and his contributions, or at least what I can reasonably discuss in the time I have. And then, like I said, after that, we'll basically do some selected topics based on what you all are interested in. And if at any point you have specific questions that kind of take us in some other direction, well, that's perfectly fine. You can feel free to pose those whenever you want, and I will do my best to cover all that I can that you're interested in. So I think that's the immediate plan. There's still a homework that I wanted to do that kind of tidies up some of the stuff between Islamic mathematicians and all the way through. I want to cover through like right before Newton and Leibniz. So there'll be a homework that covers that, and then you'll have probably just one more homework after that that will kind of deal with 17th and 18th century mathematicians. So a lot of those will be mostly writing stuff, because some of the math questions that I would have to ask you might be a little bit too involved. So it will be there'll be less computation. If there is computation, then it will be something that's not that's not too off the wall. But anyway, that's the immediate plan. So so yeah, look for that. I'll post that in a couple. I'll probably post it pretty late tonight or sometime, and it'll be due like normal in like a week. So anyway, I will see you all on Monday.